Hi, this is NeuroMo, bringing you another Machine Learning for Neuroimagers tutorial. In this video, I will discuss how to control for covariates within your model. This video will be part review of how to control for confounds and decoding analyses of neuroimaging data by Snoke et al., and a tutorial of how to implement cross-validated confound regression proposed in the study in R. The authors have kindly provided their code in Python, which can be found on GitHub. Before continuing with this video, I strongly suggest you refresh on LOS regressions. If our question is, what morphometric features are the most predictive of sex, we want to ensure confounding features, like age, are not influencing our model. To do this, you could regress out age from the entire dataset. However, this is bad practice in machine learning. When doing any transformation on your features, you should first do the transformation on your training set, and then take that same transformation used on your training set and apply it to your validation or testing set. This is necessary in order to avoid a theoretical peaking bias. Basically, this is when information from the testing set bleeds into the training set. So how should we deal with these covariates? One proposed method is to use cross-validated confound regression from Snoke et al. 2019. Not Supreme Leader Snoke, this Snoke. We'll come back to this method and how to do it in R later. First, let's cover some of the main takeaways from the study. A priori counterbalancing is very common in studies and is quite necessary in neuroimaging to ensure your results aren't due to extraneous factors in your dataset. A priori counterbalancing can be described as recruiting participants between groups in your dataset to ensure no significant differences in age, sex, or other demographic factors. In my humble opinion, this is not the goal in machine learning classification. The classifiers we train should be robust regardless of age, sex, etc., and thus must be trained on diverse, large datasets. Post-hoc counterbalancing is also done sometimes, typically with public datasets. Also a necessary step for performing a tightly controlled study. However, the same problem occurs as in a priori counterbalancing. This counterbalancing occurs after the study has completed. What Snoke and others have observed is that the observations that are left out in the counterbalance are typically the quote-unquote hard to classify observations. While this may make your classifier look good for publication, it's overfitting, thus a bad model. Thirdly, like I said earlier, any transformation you do to the data should be done within the cross-validation. First on your training set, then apply the same transformation to your testing set. Not doing this typically results in overfitting, an overestimate of your model's accuracy. In the case of a whole dataset confound regression, it results in underfitting, an underestimate of your model's accuracy. It's unclear why this is the case for confound regression. Regardless, this strongly suggests any transformations done to your features should be done within the cross-validation. These rectangles have the features width and height. If the training set has a mean height of 0.55 and a mean width of 1.47, and we want to demean our data, we would divide each training set observation, rectangles in this case, by the training set mean height and width. For the testing set, we would also divide the height and width by the mean training set height and width. This will avoid what is called a peaking bias, which would bias our classifier. Okay, before we dive into the code of cross-validated confound regression, let's get an overview of what is going on with this method. First, we're going to define our confounding feature, and in this case, it'll be age. Second, we're going to set up our k-fold cross-validation with a for loop. Thirdly, we're going to define our training and testing subsets within each fold. Fourthly, we're going to estimate the betas from the training set. Fifthly, we're going to subtract the beta estimates associated with the confounding feature from the training and testing features. And finally, we're going to put the corrected training set features into a support vector machine to be trained on, and test it on the testing set. Now that we have a good overview of what will be happening, let's jump into the code. As always, let's load in our libraries, caret and dplyr, and read in our data using the read.csv command. Also, let's eliminate any observations with no values for a feature. For clarity and my own sanity, I'm defining some data frames that we'll be using later for storing our results. K equals 10 defines how many folds we're going to do for our cross-validation, in this case, 10. Fold inner will randomly split up the dataset into 10 sections. In the console window, I'm setting j equal to 1, so I'll only run through one fold of the cross-validation for demonstration purposes. And conf will stand for our confounding variable, age. The for loop is what sets up our cross-validation. It will loop through the dataset k times, in our case, 10. Indexes defines the training and testing sets, which we can then use to subset our dataset features and confound. The xtrain and xtest matrices will only contain the morphometry features, while the ctrain and ctest matrices will only contain the confounding feature. Okay, let's estimate the betas for the training set and then subtract the beta estimates from the training and testing set features. The solve function is the one doing all the matrix maths for us. Before we can run our model, we must insert the Y feature, in this case sex, back into our data frame. Now, the model can be run, but we need a way to store our model performance metrics before moving on to the next fold in the cross-validation. That's what lines 76 through 83 accomplish. The data frame that you'll want to look at in the end is the all-conf data frame, which will have 10 values, one for each fold in the cross-validation. I'm clearing the objects in my environment, so the stored values that I've already created in the walkthrough won't affect the new ones created when I run all of the code. Okay, let's run the whole thing at once and see what happens. You can run the entirety of the code by pressing Ctrl-Alt-B on Windows or Command-Alt-B on Mac. So the accuracy is around where we had it when not doing cross-validated confound regression, which is a sign that age isn't a large confounding factor in our case. To the best of my knowledge, there isn't an objective way to tell if a feature is a significant confounding variable. If the accuracy changes a lot, it probably is, and if it doesn't change that much, it probably isn't. Also note that I'm only storing accuracy as a model performance metric, and you would want to also store specificity, sensitivity, and other metrics. I'll leave that for you to figure out how to do. Thanks for watching, and I hope now you'll be able to account for your confounds in your machine learning models.